David H. Frakes, PhD. I'm an assistant professor here at Arizona State University, jointly appointed in the schools of Biological and Health Systems Engineering and the School of Electrical, Computer, and Energy Engineering. You know, the pathology that we deal with, cerebral aneurysms, those affect approximately 2 to 5% of the population. It's unclear, exactly how many people have them because oftentimes, in the favorable cases, someone can go through life having one and not even know it if it doesn't become problematic. When there is a problem, when an aneurysm does develop and sometimes eventually burst, then the outcomes are usually catastrophic. The mortality rates are on the order of 50% in the first few days, and overall, cerebral aneurysms, ruptured cerebral aneurysms specifically, cause about 20,000 deaths each year in the United States. An aneurysm is a balloon-like sac that forms off of the side of a blood vessel. We think of our blood vessels as tubes, and if there's a weak point, then a balloon can come out of that tube and expand out from the vessel where it shouldn't be. That's what an aneurysm is. Now, what an aneurysm does when it bursts is it allows blood to flow out of the cerebrovascular system, out of the blood vessels in the brain, and into the brain tissue itself, where it's not supposed to be. The heart is a very strong muscle. So when we have the heart pumping blood out of the blood vessel and into brain tissue where it shouldn't be, brain tissue, of course, being surrounded by the skull, which is an enclosed space, the pressure there gets very high very quickly, and the heart effectively pumps blood into the brain where it crushes the brain tissue, which causes fatal catastrophic injury in most cases. There are a lot of really amazing and extremely effective devices for treating these vascular pathologies. The problem is that, for the most part, we don't really understand what the specific effects are that these devices have. Oftentimes they work, but many times they don't. And the problem is we don't really understand why they don't work when they don't work. So what we do in my lab is we take these devices, we put them into models of cerebral aneurysms that come from real people, and then we then find out exactly what the devices do in terms of altering fluid dynamics in the affected blood vessel. With that information, we can understand specifically what each device does and therefore plan for using it more effectively in the clinic.
My name is Justin Ryan. I'm a graduate research associate here at Arizona State University in the Image Processing Applications Laboratory. On a daily basis, I run both computer and physical modeling aspect of the lab, and that entails the creation of either blood vessels or even cardiac structures in a computer form as well as a physical form. This big initiative we're working on is part of the cerebral vascular modeling component. So what we need to do is we want to create models from patient data of cerebral aneurysms. And we do this through a process that involves many hospitals as collaborators, all the way to rapid prototyping using Solidscape equipment, to metal casting, and then finally urethane or plastic casting.
I'm Dr. Bree Roselle. I am a postdoctoral researcher here at the Image Processing Applications Lab. The major overall goal for us is actually to use the experimental methods to validate computational methods. The issue with these kind of things is that computational studies aren't validated in a way that we're very confident with what they're telling us. And so what we can do is use the information we get from the experimental studies, because we know our validation techniques are good and that we have carefully made sure that our flow is similar to what we would see in a patient. We know exactly what's happening in our experimental studies. We can use that to validate the computational studies.
The value of being able to print models and actually build anatomically accurate vascular geometries to test, the ground truth that comes from that process is really invaluable in our research. The end product of our physical 3D modeling stage is a transparent block wherein there is a lost core or a hollow portion of the model that is an exact replica of a cerebral aneurysm from a person. In order to get to that end product, we start off by building the positive, the actual geometry from the patient. And then we then mold another material around that so that we can create a transparent block with the lost core portion, with the hollow portion representing the blood vessel. So rapid prototyping is how we get that first, that positive, before we go to the negative that is the flow model.
The ability to pull these geometries out and just send them to a printer, I mean, it seems like magic almost, but it's just the best way for us to be able to quickly make a model of a patient's geometry. And I was giving a tour to high school students the other day and showing them the models, and they're just amazed that we can do it. This technology is outstanding, and it allows us to really do things that we want to quickly and effectively.
Another thing that we're using 3D printing for is for creating replicas of congenital heart defects for surgical planning. So we've initiated a project where instead of walking in and to an operation after looking at several images on a screen, a surgeon can walk into the operating room holding a real replica of a congenital heart defect that describes what they're going to see when they actually open a patient up and go to fix it. So this is another instantiation of 3D prototyping having just a really high value in medicine and bioengineering. It simply allows us to express data in ways that were impossible 10 years ago. In both the near and midterm, I think that we're all going to be surprised by the incredible number of places that 3D printing fits into both medicine and medically oriented research. The truth is that we're only now starting to understand how useful it can be in all the different places it can fit. Because we've gotten very accustomed to using computer representations of things, and those have their advantage, there's no question. But at the same time, as humans, we're used to putting our hands on things. We're used to looking at things in the real 3D space that we experience. Rapid prototyping allows us to leverage the most natural of our skills in looking at objects by creating just about anything in the form that we can appreciate it most naturally. Our Solidscape machine is the backbone of our modeling process. We use that to build the cores, to build the blood vessel models that we then translate into transparent flow models for our experiments. So all of the ground truth data that's informing our simulations in the end, it comes from these models that the Solidscape machine helps us build. For me personally, the prospect of actually using math and science to improve quality of life is the driving factor. That's what excites me about research. It's what's drawn me to bioengineering. And to be able to use skills that I'm naturally interested in terms of mathematics, in terms of science, experimentation, simulation, things that I have a natural passion for, to be able to employ those and purpose those so as to improve human quality of life is the most compelling factor behind what I do.